This is a Calculus AB multiple choice solution guide. We're going to go through section 1, which has about 28 questions, and you may not use a calculator on this section. If you enjoy these videos, please make sure to subscribe, like the video, or post a comment down below. Let's get started. The first question says, if y equals x sine of x, then dy of dx is equal to. So here we want to use the product rule. So we first do, if we have y equal x sine x, we say like x is equal to that. We'll say u is equal to x, and v is equal to sine x. So u prime is equal to 1, and v prime is equal to cosine of x. So to use the product rule, we have that dy dx is equal to the first value here, so u times v prime plus v times u prime, which is equal to x cosine x plus sine x. And this answer here is B. All right. On to the next one. We have let f be the function given by f of x equals 300x minus x cubed. On which of the following intervals is the function f increasing? So f is increasing whenever the derivative f prime of x is greater than or equal to 0. So we solve for f prime of x, taking the derivative. So we get f prime of x is equal to 300 minus 2x squared. And we set this greater than or equal to 0. So we have negative 3x squared. Negative 3x squared is greater than or equal to negative 300. You have x squared is less than or equal to 100. So you have x is either less than or equal to 10, or x is greater than or equal to negative 10. So our answer is B. All right. Now we have the derivative, or so the integral of secant x tan x is equal to, we're trying to find the derivative of secant x tan x. This one, you really just need to know your trig derivatives. So it just so happens that d dx, a derivative of secant x, is equal to tan x secant x. So our integral of secant x tan x dx is equal to secant of x plus c. The answer is A. 4. So if f of x equals 7x minus 3 plus ln of x, then f prime of 1 is equal to what? So here we take the derivative of f of x. So we have f prime of x is equal to 7 plus 0 for derivative of negative 3 plus 1 over x for the derivative of ln of x. Then we plug in 1, so f prime of 1 is equal to 7 plus 1 over 1 is equal to 8. So our answer is E, 8. Okay, so here we're given a graph. It says the graph of the function f is shown above. Which of the following statements is false? So here we have, we'll just go through each question or each bullet. So we have the limit of f of x approaches 2 exists. So if we look at x equals 2, both from the negative direction and the positive direction, they approach the same value. So the limit does exist. So this is true. Now B, the limit as x approaches 3 of f of x exists. So now we look at x equals 3. So the same thing. So from the positive direction and the negative direction, they both exist and they approach the same value. So this is true. The limit as, go on to C. So the limit as x approaches 4 of f of x. Well, here we have that as from the positive side, it goes to 2, and the negative side, it comes down to, so in the positive direction, it goes to 2, in the negative direction, this one, we have a graph. So this is the graph of the function f is shown above. Which of the following statements is false? So we're going to look at each statement and check if it's true or false. The first statement says the limit of f of x as x approaches to exists. So for a limit to exist, it needs to approach the same value from both sides. So if we look at x approaching 2, both sides approach the same value, so this exists. That's true. Now if we go on to b, x approaches 3. If you look at 3, both sides of the line approach the same value, so that limit exists. Now if you go into c, so the limit as x approaches 4, at x equals 4, both sides of the equation do not approach the same value, so this is not true. It's most likely the answer, but let's just check the others. So d, at the limit as x approaches 5, at 5, both sides approach the same value, so that is true. And e, the function of f is continuous at x equals 3. So something to be continuous, the limit from both sides needs to approach the same value, and the value at that point needs to be the limit from both sides. And that is true as well. So the answer here is C. Okay. On to 6, a particle moves along the x-axis. The velocity of the particle at time t is 6t minus t squared. What is the total distance traveled by the particle from time t equals 0 to t cubed? So we're given a velocity equation. V of t is equal to 6t minus t squared. And now to find the total distance traveled, this is going to be an integral. So the distance is equal to the integral from t equals 0 to 3 of 6t minus t squared. So now we evaluate. This integral happens to be 3t squared minus t cubed over 3 from 0 to 3. We plug in our values. We have 3 times 9 minus 27 over 3. And then when we plug in 0, we get 0 for everything. So this is all we have to solve for. We have 27 minus 9 is equal to 18. So the answer here is D, 18. Now we go to 7, y equals, in parentheses, x cubed minus cosine x all to the 5th. So we're asked to solve for y prime. So here we want to use the chain rule. So first, we unlayer everything by taking the first derivative by decreasing the exponent. So we get 5 times x cubed minus cosine of x all to the 4th. And now we multiply this by the derivative of the inside. So it's d dx of x cubed minus cosine of x. So we get 5 times x cubed minus cosine of x to the 4th times, the derivative of this inside happens to be 3x squared plus sine x. And looking at this answer, we see that it matches up with E. So the answer here is E. All right, so now on to the next one. We have a tank, contains 50 liters of oil at times t equals 4. Oil is being pumped into the tank at a rate R of t, where R of t is measured in liters per hour and t is measured in hours. Selected values of R of t are given in the table above. Using a Wright-Riemann sum with 3 subintervals and data from the table, what is the approximation of the number of liters of oil that are in the tank at times t? So 2 key points here. We're using a Wright-Riemann sum, and they want us to use 3 subintervals. So we're told that at t equals 0, there's 50 liters, and we want to use 3 intervals, 1, 2, 3, to approximate the number of liters at t equals 15. So now, just to draw out what our Riemann sums look like, right? So you're probably aware there's right Riemann sums, left Riemann sums, and middle Riemann sums. So let me plot 4, 7, 12, and then 15, and this kind of looks something like this. Yeah. So right Riemann sum means that for every subinterval, so our subintervals are 1 from 4 to 7, so 1, and another one from 7 to 12, another from 12 to 15, we use the right value of each interval for the height. So we use this one, this one. So for our first box, we use the height at t equals 7, For the second one, we use the height at t equals 12. And for the third one, we use the height at t equals 15. And we know that we start off with 50 liters. So the approximation here would be 50 plus 3, the difference of the base for the first interval, so 3, times the height at t equals 7, which is 6.2, plus the next base, which is 2, times the height at t equals 12, which is 5.9, plus the next base, which is 3, plus the height at t equals 15, which is 5.6. So we get 50 plus 18.6 plus, this is 5. So it's 12 minus 7, which equals 5. Yeah. Which is 29.5 plus 16.8. And if you sum all these together, you get 114.9. So the answer here is C. Okay. So the next question says, let f be the function defined above. For what value of k is f continuous? F continuous at x equals 2. So remember, to be continuous, the limit as x approaches a value a from the positive side should equal the limit as x approaches a from the negative side, which should equal the value at that point, f of a. So here we need to find the limit as x approaches 2 of f of x, and this should be equal to f of x, right? So we know that from this piecewise equation, f of x when x is equal to 2 is just k. So we want the limit as f of x approaches 2 to be equal to k. So now we just need to solve the limit. So the limit as x approaches 2 of f of x, you plug in the equation. So here it's 2x plus 1, x minus 2 all over x minus 2. And the reason we use this equation here for the limit is because as we're approaching x equals 2, we're not at x equals 2. So we need to use this equation. Now to solve this limit, we see that in the numerator and denominator, we can cross out those two values. So we see that it is equal to 2x plus 1. And now we can plug in our value of 2 for x. So we see that this is equal to 2 times 2 plus 1 is equal to 5. So we know that f of 2 now must equal to 5. So that means that k is equal to 5. So the answer here is E. Right, moving on to 10. So this one says, what is the area of the region in the first quadrant bounded by the graph of y equals e to the x over 2 and the line x equals 2? So we're looking for area. So we know we need to use an integral, but it's always good to quickly try and draw out the lines so we make sure we find the integral of the right region, right? So one of the lines is x equals 2, which is a vertical line, something like that. And the other one is y equals e to the x over 2. So let's just plug in a few values to get like points that would be on this line. So y at 0 is e to the 0, which is equal to 1. Y of 1 is e to the 1/2, which is equal to the square root of e. And y of 2 is e to the 1, which is just e. So this tells us that our second line is something like that, with a little bit of a curve. So our area is everything in here. So now that means that to solve this, we need to find the integral from 0 to 2, integral from 0 to 2 of e to the x over 2 dx. So now to integrate this equation, we remember that the derivative, sometimes it helps think of the derivative. So the derivative of e to the value kx is equal to ke to the kx. So we now have e to the x as a 1/2. So the integral of this just happens to be 2e to the x over 2. And you can test this out by taking the derivative of this, which would be 1/2 times 2e to the x over 2. So we integrate this from 0 to 2, which gives us 2 times e to the 1 minus 2 times e to the 0, which equals 2e minus 2. So the answer is A. All right, so on to question 11. Let f be the function defined by f of x equals the square root of the absolute value of x minus 2 for all x. Which of the following statements is true? So for this one, it also helps to just quickly plot it out so you have something to visualize. So this, we know that it changes around x equals 2. So when x is equal to 2, this comes out to be 0. And then it's a square root function. So if you remember, like f is equal to the square root of x looks something like that. But it's also an absolute value. So whenever x, this inside part is negative, it becomes positive. So this just happens to look something like this. Yeah, all right. So let's look at each statement. The first statement says that f is continuous but not differentiable at x equals 2. So this is continuous because the limit from both sides approaches the same value, and they both, that limit is equal to that value at that point. And looking at this, it doesn't look like we can differentiate it, because what would the slope be at this point? So to be honest, this one looks true. But let's just check the others to make sure we didn't make a mistake. So now we have that f is differentiable at x equals 2. Well, this is not possible, because if you can look here, we can't get a slope at that point. Then we have f is not continuous at x equals 2. This is definitely not true, because like I said, the limit from both sides equals the same value, and that is equal to the value at that point. So it is continuous. The limit as x approaches 2 of f of x does not equal 0. This is not true, because the limit as it approaches 2 from both sides is 0. And we have x equals 2 is a vertical asymptote of the graph of f. There is no vertical asymptote here. Nothing that approaches some vertical line. So that is definitely not true. The answer here is A. All right, so now for 12, using the substitution of u is equal to the square root of x, the integral from 1 to 4 of e to the square root of x over the square root of x dx is equal to which of the following? So now whenever we have a u sub, we need to plug in our value of u, but also our value of du. So it helps once you know what the u is, it also helps to solve for du. Right? And just to make this easier, I'm going to rewrite my u as x to the 1/2. So with u being equal to x to the 1/2, du is now the derivative of x to the 1/2, which is 1 over x times x to the negative 1/2 dx. Right? So that's implicit differentiation. And I'm just going to simplify this by writing it as 1 over 2 times the square root of x dx. Yeah, okay. So now we can start plugging in our u into our integral to find what it should look like with the u substitution. So for the bounds, now the original bounds 1 and 4 were in terms of x. So if we're going to make a du, we need to have it in terms of u. So the starting bound will be the square root of 1, and the upper bound will be the square root of 4. And that's coming from u equals the square root of x. Then we go in a little bit. So we know that u is equal to the square root of x. So this becomes e to the u. And here, I'm not sure yet how I, like you could just plug in u for this square root of x down below, which is perfectly fine. But then you're left with this dx, right? So you can't just change that dx to be du. And what we need to do now is using the du that we solved for above, which gives us a dx, we now need to plug this back in to replace this dx with du. So we're first going to rewrite this dx so we get just dx alone. We're going to isolate dx. So it just so happens that this becomes 2 square root of x du. And I want to get rid of all these x's. So we know that u here is equal to the square root of x. So we're going to say that dx is equal to 2u du. So now that I have this, I can plug this dx in here. So I'm given the square root from 1 to 2 e to the u over u times 2u du. And if I simplify this, I get the integral from 1 to 2 of those u's cancel, 2 e to the u du, which is equal to c. So the answer here is c. Okay. Now on to 13. The function f is defined by f of x, which is a piecewise function. What is the value of the integral from 1 to 5 of f of x dx? So we start by splitting this integral using the piecewise function. So f of x dx. So we have two bounds. So the first one will go from 1 to 3 of f of x between 1 and 3, which is just 2 dx, plus the integral from 3 to 5 of the next piecewise function, x minus 1 dx. So this is equal to 2x from 1 to 3 plus, so now if we integrate x minus 1, that's x squared over 2 minus x, 3 to 5. So if we solve this out, we get 2x when we plug in 3 is 6, 2x when we plug in 1 is 2, so 6 minus 2, plus x squared over 2 is 25 over 2, minus 5, minus 9 over 2, minus 3. So this is equal to 4, plus, so I'm going to group these terms. So I'm just going to do 25 over 2 minus 9 over 2, which is 16 over 2. And then we have minus 5 minus 3, which is minus 5 plus 3, it's minus 2. So this comes out to be 2 plus 8 is equal to 10. So our answer is D for 10. Now going on to 14, we have if f of x is equal to the square root of x squared minus 4 and g of x is equal to 3x minus 2, then the derivative of f of g of x is at x equals 3 is equal to what? So here you might be tempted to find the composite function, so plug in g of x for f of x, simplify it, and then take the derivative. You could do it that way, you might get the right answer, but a simpler way is to keep them as variables and then take the derivative without plugging things in. So what do I mean by that? F of g of x here is g of x substituted in wherever we see x. So this is equal to g of x squared minus 4 all to the 1/2, right? I'm going to leave it like that. And then we have g of x, which is equal to 3x minus 2. And when I take the derivative of this, I know I'm going to need to use the chain rule, and I'm going to have to keep taking the derivatives of the inner portions. So I'm also going to preemptively solve for g prime of x, which just so happens to be 3. Great. Okay. So now the derivative of this composite function, so f prime of g of x, is, so we use our chain rule. So here I bring down this 1/2. I get 1/2 times g of x squared minus 4 all to the negative 1/2. Now it's times the derivative of the inside, which is 2 times g of x, and then times the derivative of the inside of that is g prime of x. All right. And now that I have this, I'm actually just going to stop here because this represents the derivative f of g of x. And I'm being asked to evaluate it at x equals 3. So I'm going to solve this for x equals 3. So the first thing I need to do is find g of x when x is 3, so that's g of 3. So g of 3, bouncing up here again, is equal to 3 times 3 minus 2, which is 7. So I'm looking for f prime of g of 3 is equal to 1 over 2 times that g of 3, which is 7, so 7 squared minus 4 to the negative 1/2, times 2 of g of 3, which is 7, times g prime of x, which is g prime of 3, which happens to be 3. And I know that from up here. And now I just simplify. So this is 1/2 times 7 squared, which is 49. So 45 to the negative 1/2 times 2 times 7, which is 14, times 3. So now this is equal to 14 times 3 is 42. So 42 over 2 times 45 to the negative 1/2, which is equal to 21 over the square root of 45. If I factor out that 45, I get this is 21 over the square root of 9 times the square root of 5. Square root of 9 is 3, so I'm left with 7 over the square root of 5. So the answer here is A. So moving on to 15, we're given a graph of f. It says the graph of a differentiable function f is shown above if h of x is equal to the integral from 0 to x of f of t dt, which of the following is true. So we're just going to pause and think about what h of x is. H of x is the integral of f of t, which is the area under the curve of f of t. So h of x is represented by this shading. And if we put that into words, it's equal to the area under the curve of f from 0 to x. So now we're asked to find which of the following, which statement or which ordering here is true. And we're looking at h of 6, h prime of 6, and h double prime of 6. So let's first look at h of 6. So h of 6 is the area under the curve of this function f from x equals 0 to 6. And this whole region is negative. So we know that this is negative. Right. So now for h prime of 6, this is where it gets interesting. So if we look at our equation where it says h of x is equal to this integral, h prime is the derivative. So the derivative sort of cancels out this integral. So we can sort of say that h prime of 6 is equal to f of 6, and f at 6 is 0. So we know that h prime of 6 is 0. Now for h double prime of 6, this is equivalent to f prime at 6. And f prime is the slope of our line f. And here the slope is positive. So my ordering is that h prime of 6 is greater than h double prime of 6 is greater than h prime of 6, which is greater than h of 6. And that answer is A. Okay, let's move to the next problem. 16. A particle moves along the x-axis with its position at time t given by x of t equals t minus a times t minus b, where a and b are constants and a does not equal b. For which of the following values of t is the particle at rest? So for the particle to be at rest, it means that it's not moving. So x prime of t needs to be equal to 0. The derivative of x of t needs to be equal to 0. So to solve for this derivative, we have the product of two values, so we're going to use the product rule. So we have x prime of t is the derivative of the first, so derivative of t minus a just happens to be 1 times t minus b, plus the derivative t minus a times derivative of second, which is just 1. And we set this equal to 0, and then we solve for which values of t make this true. So to solve this out, I'm going to just unwrap these. You'll notice that everything is just being added. So I can simplify this to be 2t minus b minus a is equal to 0. So I get 2t is equal to a plus b, and t is equal to a plus b divided by 2, which happens to be b, and that's the answer. Okay, now on to 17. So we're given a graph of f, and the question says the figure above shows the graph of f. If f of x is equal to the integral from 2 to x of g of t dt, which of the following could be the graph of y equals g of x. So we want something that represents g of x. And the key here is that the graph that they've given to us is actually the integral of g of t dt. So in a way, g of x is equal to the derivative of f of x, right? So, and the way you can think of that is, so f of x is equal to the integral of g of x. So if I take the derivative of both sides, it sort of cancels out this integral, and I'm left with f prime of x is equal to g of x. So thinking about it this way, now I need to figure out which one of the graphs below, A, B, C, D, or E, is the derivative of this graph of f. And if you remember, derivative gives us the slope. So if we look here, the slope of this line is constant, right? So slope is constant. And it's also positive, right? So the slope of this line, right, it's positive and positive. So I'm just looking for a graph that has a constant value, right? So the slope at every point is constant and it's positive, which just happens to be A. And if we look at the other solutions, just to make sure we didn't get it wrong, B is also constant, has a constant slope or constant value, but it's negative. And then all the other options, they're not constant, right? So the answer here is A. On to 18. So we have the limit as h approaches 0 of ln of 4 plus h minus ln of 4 all over h is what? So when we do these limits, the first thing we do is we plug in the limit that we're approaching, which is 0. So we have that ln n of 4 plus 0 minus ln of 4 all over 0. So this comes out to be ln of 4 minus ln of 4, which is 0, all over 0. Huh. So what do we do here? Now, you might be tempted to say non-existent, but whenever we get a limit that is 0 over 0, it does not immediately mean that the limit is non-existent. Here, we need to use something called L'Hopital's rule, which pretty much says when you get a limit that's 0 over 0, you take the derivative of the top and the derivative of the bottom, and you find the limit of that. So the derivative of the top here of ln of 4 plus h minus ln of 4 with respect to h happens to be 1 over 4 plus h. And this is because the derivatives d dx of ln of x is equal to 1 over x. Right? So going back to our derivative, so we get ln, 1 over 4 plus h time minus the derivative ln of 4. This is a constant, which is 0. And we put that all over the derivative of the bottom. So the derivative of h with respect to h is just 1. So it's equal to 1 over 4 plus h. And we find the limit of this. And so the limit as h approaches 0, 1 over 4 plus h is just 1 over 4. And that's our answer. The answer here is B, 1 over 4. Yep. 19, the function f is defined by f of x is equal to x all over x plus 2. What points x comma y on the graph of f have the property that the line tangent to f at x comma y has slope 1/2? Okay, so here we want to find the points x comma y that have a slope 1/2. And whenever we see slope of an equation, we think derivative. So we need to find the derivative of f, which is f prime of x. And here we have a quotient, so we're going to use the quotient rule. I'm going to set my u equal to x and my v equal to x plus 2. So my u prime is 1, my v prime is also 1. Okay, so now f of x, if you remember from the quotient rule, this is equal to low, so the v, d high, which is u, minus high, which is u, derivative of low, which is v, all over v squared. So now plugging in values, I get x plus 2 times 1 minus x all over x plus 2 squared. And I want to find when this is equal to 1/2, because it means that at these points the slope is 1/2, right? So let's simplify a bit. In the numerator here, I have x plus 2 minus x. The x's cancel, so I'm just left with 2. So this is equal to 2. And then I'm going to get rid of my quotient by multiplying both sides by x plus 2 squared. So it's equal to 1 over 2 times x plus 2 squared. And then I'm going to multiply both sides by 2, so I get 4 is equal to x plus 2 squared. Now if I unravel that the square by taking the square root, I get that plus or minus the square root of 4 is equal to x plus 2. So I have plus or minus 2 to x plus 2. And when I solve that out, I get x is equal to 0 or negative 4. And I find that there are two solutions or there's one solution that has those x values, which is c. And just to make sure everything comes out right, if I plug in x equals 0 into my f of x equation, I do get 0, so the point 0, 0 exists. And then when I plug in negative 4 for x to this equation, I have negative 4 over negative 4 plus 2, which is negative 4 over negative 2, which is equal to 2. So the math checks out, and my answer is C. On to 20. Let f of x equals 2x plus 1 cubed, and let g be the inverse function of f. Given that f of 0 is equal to 1, which is what we're looking for, what is the value of g prime of 1? Okay, so inverse functions is where we switch x's with our y's, right? So the original function we have is like y equal to 2x plus 1 cubed. So now the inverse of this is where I flip my y's and my x's, so I get x is equal to 2y plus 1 cubed. And I want to solve this for y. So the first thing I'm going to do is bring down the cubed. So I get cube root of x is equal to 2y plus 1. Now I isolate the y. So I get the cube root of x minus 1 is equal to 2y. And then I get, divide both sides by 2. So the cube root of x minus 1 all over 2 is equal to y. All right, and this y, that's my inverse function, so this is the g of x. Perfect. So now I need to find the derivative of g of x. So g prime of x is the derivative of what we just solved for. And here, I like to, what I'll start with is rewrite the equation so it's easier to take the derivative. So I'm going to say g of x is equal to, root of x minus 1. So I'm going to say g of x is equal to x to the 1/3 divided by 2 minus 1/2. So that's the same thing as what we had here. I just wrote it as a fraction exponent. It just makes it easier to take the derivative. So now when I solve for g prime, I take first find the derivative of this first value here. So I get 1 over 3 is x to the 1/3 minus 1, so it's negative 2/3, and I still have that 2. And the derivative of minus 1/2 is just 0, so that goes away. And now I can just plug in 1 for my x. So I have g prime of 1 is equal to 1 to the negative 2/3 all over 6. And 1, really, to any exponent, just comes back out as 1. So I get 1 over 6. And that's D. So the answer here is D. Perfect. Now on to 21. We have the line y equals 5 is a horizontal asymptote to the graph of which of the following functions. So here we're being asked to solve for a horizontal asymptote. And if you remember, horizontal asymptotes have this shape where a line approaches some horizontal value, right? So it could be like, right, something like that. And the key unique feature about a horizontal asymptote is that as your equation approaches some infinity, negative or positive, it will approach that asymptote. So what we're really being asked to look for here is which of these equations, y, have a limit where x goes to infinity such that y is equal to their asymptote, which is 5. So all we need to do is solve for the limits as x goes to infinity for the options that they've given to us and see which one has a limit of y equals 5. So let's solve these limits. For the first equation, we have sine of 5x all over x. So now a sine function, it has like max and a min. It doesn't get very large, but x in the denominator will get very large. So the limit here as x approaches infinity would just come out to be 0 because x would get really large and this would stay as some periodic value comes out to be 0. And now this limit for b as y goes to 5x would be infinity because we'd have 5 times some infinitely large number which remains very large. For c, we have 1 over x, which would be an infinitely large number, minus 5, which is still infinitely large. So we have 1 over some really large number, so the limit here would still be 0. For d, we have 5x over 1 minus x. And so now we have the same term, both the top and the bottom, x and x. So to find the limit here, so this limit, what we do is we find the biggest and fastest growing term on both sides. So we have 5x on the top, and we have minus x on the bottom. And then we can cancel out these x's, and what we're left with is negative 5. So the limit here is negative 5, which is close to what we want, but it's not what we want. So the answer is likely e, but let's solve e to make sure. So here we have y equals 20x squared minus x all over 1 plus 4x squared. So again, we have a polynomial. So the limit of these polynomials as we go to infinity, we just look at the largest terms, the top and the bottom. So this one would be the limit as x goes to infinity. The largest term at the top is 20x squared. Largest term at the bottom is 4x squared. These terms are the same, so they cancel. And we're left with 20 over 4, which happens to be 5. And that's exactly what we were looking for. So the answer here is E. Okay, on to the next one. 22. Let f be the function defined by f of x is equal to ln of x over x. What is the absolute maximum value of f? So when we're looking for absolute maximum, let's just say we had some equation that looks like that, right? If we're looking at the absolute maximum, you'll notice that there's a few values that we need to test when we have the equation. We need to test the endpoints, and then we need to test the critical points in between wherever the slope is 0. And the reason we need to do this is if instead of a graph that looked like this, if we had something that looked like that, well now at the endpoints, it's not very large, but the maximum occurs at this critical point. So we need to test the endpoints and the critical points and see which one gives us the largest value. All right. So now the endpoints of this equation are just negative infinity and positive infinity. And just looking at this, so we have ln of x over x. Now ln of x does not grow nearly as fast as x does. So if we have a negative infinity in the bottom or a positive infinity in the bottom, for both these values, f of x just approaches 0. So the limit as this goes to infinity, either way, f of x is just 0. So let's now find the critical points and see if we get a larger value. So to get the critical points, we need to solve for the derivative and find when that's equal to 0. Now the derivative ln of x over x, again, we would use the quotient rule here. So I'm going to first define my u. So u is equal to ln of x. U prime is 1 over x. My v is x. My v prime is 1. So f prime of x is equal to so v u prime minus u v prime all over v squared. I plug in, So I get x times 1 minus u ln of x times 1. Get that right? Oh, sorry. I did that. Plugged that in wrong. So I get v, which is x times 1 over x for u prime, minus u, which is ln of x times v prime, which is 1, all over v squared, which is x squared. Okay. Now I want to find when this whole thing is equal to 0. So let's simplify it a little bit. In the top here, these x's cancel out, so I'm left with, 1 minus ln of x all over x squared is equal to 0. So now I can multiply both sides by x squared. So one solution is x squared is equal to 0, but that just means it's undefined. So what I get is that 1 minus ln of x is equal to 0. So my critical point is really when 1 minus ln of x is equal to 0. So let's solve for when that happens. I'm going to start by isolating the x. So I get 1 is equal to ln of x. And if you remember how to unravel these logs, you raise what it's equal to, so in this case, a natural log. So I raise this to be e to the 1 is equal to x, right? And any number to the first power or comes out as itself here. So this would be x is equal to e. And this is when the critical point occurs. So now I take this x equal to e and I plug it back into my f of x equation and I find out what that value actually is, right? What the y value is. So f of e is equal to ln of e all over e. Natural log of e is just 1. So this is equal to 1 over e. So now we have our critical point, which is 1 over e, which is a positive number. And then at the two extremes of negative infinity, infinity, it just approaches 0. So the maximum value here happens to be 1 over e, which is b. Right. Now on to 23. If p of t is the size of a population at time t, which of the following differential equations describes linear growth in the size of the population? So linear growth means that we are growing at the same rate, right? So at t equals, the difference between t equals 0 and 1 is the same as the difference between t equals 1 and 2, and so on. So the rate of change is constant. And what that really means is that the derivative is constant. And this occurs when dp over dt is some constant value that doesn't change over time. And the only option where that is true is A. dp over dt is equal to 200. Okay. 24. Let g be the function given by g of x equals x squared times e to the kx, where k is a constant. For what value of k does g have a critical point at x equals 2/3? So we're looking for a value of k that gives us a critical point at x equals 2/3. So the first thing is critical points are when the derivative, so g prime of x, is equal to 0. So what we're looking for is a value of k that makes g prime of 2/3 equal to 0. Right? So let's first start by solving for g prime of x. So g prime of x. Here we're going to use the product rule. So we'll do x squared times the derivative of that second part. And the derivative of e to some power is it's the derivative of that exponent. So the derivative of kx is k times that same power. It stays the same. So k e to the kx. And now I do so the other part of my product rule. So derivative of the first part, which is 2x times e to the kx. So you can see now all you need to do is plug in 2/3 for x and then solve for the value of k that gives us a result that's 0. So g prime of 2/3 is equal to 2/3 squared, which is 4/9, times k e to the 2 over thirds x plus 2 times 2 thirds, which is 4 over 3 e to the 2 over thirds x. Okay, now I've got a bunch of terms. Oh, and again, I want to set this equal to 0. So we have a bunch of terms, and at first it seems like how would you even solve this? But one thing that we observe is we have e to the 2 thirds x in both of these terms. So let's pull that out. We had e to 2 thirds x times 4 over 9k plus 4 over 3 is equal to 0. And I can essentially just divide out this term now. It'd be one of the solutions, but you notice there's no k in there, so I don't really care. So I can get rid of that term by dividing it out, and then I'm left with 4 over 9k plus 4 over 3 is equal to 0. So if I solve for this, I get 4 over 9k is equal to negative 4 over 3. So I have k is equal to negative 3. So I look up here, the answer is A, negative 3. Okay, let's go to the next question. Which of the following is the solution to the differential equation dy dx is equal to 2 sine x? So we're given dy dx, and we're looking for the equation y equals something, right? So here we need to take the integral. The reason why is if we have y, then d dx of y is dy dx. But when we're given dy dx, to get y, we need to solve for the integral of dy dx dx, and that gives us y. Okay, so the integral of 2 sine x dx, and again, this is a definite integral, is equal to negative 2 cosine of x plus c. And to be honest, when I solve these integrals, I'm sort of like guessing it and then checking if the derivative is equal to what I want. So the derivative of cosine x is negative sine x, which gives me this, and that's how I got there. Okay, so I get that y is equal to negative 2 cosine of x plus c, and you need this c here because this is an indefinite integral. So now we need to solve for c using the value that they've given to us. So y of pi is equal to 1 is equal to negative 2 times the cosine of pi plus c. Now if you remember your unit triangle, cosine of pi is in it's over here, so that's negative 1. So it's negative 2 times negative 1 plus c. So I get 1 is equal to 2 plus c. This means that c is equal to negative 1. And that means that my answer is E, right here. Y equals negative 2 cosine x minus 1. Okay. Now on to 26. Let g be a function with first derivative given by g prime of x is equal to the integral from 0 to x e to the negative t squared dt. Oof. Which of the following must be true on the interval? So for this one, I need to figure out some properties of this equation. I like to just read through first to understand what are some things I need to understand. So I need to figure out if g is increasing or decreasing, so that's the first one. And then I need to also understand some concavity. Okay, so let's first focus on increasing or decreasing. The good thing is they've given us a equation for g prime. So remember, g prime gives us the slope, because the derivative, it gives the slope of g. So if g prime is positive, it means that the slope is positive, which means it's increasing, which means g is increasing. So all I need to do is come up with try and figure out if g prime of x on this interval is positive or negative. And what helps here is the value that we're integrating here, which is e to the negative t squared. This, if we think about it, it's e to an exponent. And e to an exponent, no matter what the value is always positive. And this is true because even if x is a negative number, e to a negative exponent is just 1 over e to the exponent. So it's just something that will get closer and closer to 0, but it'll always still be above 0. Now noting this inner term here in this boundary from 0 to 2 is always positive. So now when I integrate, remember that an integration is the area under the curve, right? So if my values on my curve, which is this e to the negative t squared, are positive, it means my area under the curve is also positive. So I know that g prime of x is always positive between 0 and 2. So right off the bat, I can eliminate any of the statements where g is decreasing, because it's not. Since g prime of x is positive, it's increasing. So now all I need to figure out is concavity. Is this concave up or concave down? So now concavity we can find from the second derivative of the function g. So g double prime of x. And here, since g of x is the integral of this function, g double prime of x is the derivative of this, which gets rid of that integral. So I'm left with g double prime of x is equal to e to the negative t squared, or x squared. And we already established that e to an exponent here is always positive. So that means, that tells us that this is positive. And whenever the second derivative is positive, this means that it's concave up. So the answer here is A. Now, if you're struggling with this part here, like how do I know it's concave up? I'll be releasing more videos that talk about the concavity from derivatives to help you visualize it. But for now, you just need to know that if the second derivative is positive, it is concave up. And if the second derivative is negative, it's concave down. Okay. So now the next question, 27. If x plus 2y times dy dx is equal to 2x minus y, what is the value of d squared y over dx squared at the point 3 comma 0? Okay, so I'm given a first derivative and I need to find the second derivative. So the way I do this is by isolating dy dx, and then I take the derivative of that. So to isolate this, I get dy over dx is equal to 2x minus y all over x plus 2y. So now the derivative of this, which I can write as dx of dy dx, is equal to dx of 2x minus y plus 2y. Yeah. So the important thing to be careful of here is this is going to involve implicit differentiation. The reason why is we have an equation where the derivative of y depends on x, and vice versa. So let's walk through this, and I think you'll understand. So now I have a quotient here. So I'm going to use the quotient rule. So I'll set this up. So my top will be u, which is 2x minus y. So my u prime here. So it's my u prime, which is my derivative with respect to x, is 2. Because the derivative of 2x is 2. But now my derivative with y to respect to x is y prime. That's not just some constant that goes away. Y depends on x. Now we have the bottom, which is v. So that's equal to x plus 2y. So my v prime is derivative of x, which is 1, plus 2 times y prime, because y depends on x. Right? Okay, so now my d squared y over dx squared, using that quotient rule, is the bottom. So x plus 2y times the derivative of the top, which is 2 minus y prime, minus, let me move all this down. Yep. Minus the top, so it's 2x minus y times the derivative of the bottom, 1 plus 2y prime, all over the bottom, which is x plus 2y squared. All right, so now I got something really big, but I found my second derivative of y, And before I even try and simplify this, you note that they've given us a point to plug in. So we can just start plugging in this point instead of simplifying it. We'll get there faster. And so we're given x and y, which allows us to plug in for most values, but we have this y prime. And what you'll notice is this y prime is dy dx, right? So dy dx is equal to y prime. And if I plug in the point 3 comma 0 into this equation, that gives me the value for y prime. So x is 3, be 6 minus 0 over 3 plus 0. So y prime is equal to 2. So now I have all the values I need. Let's start plugging it in. So I have up on the top 3 plus 2 times 0, which is 3, times 2 minus y prime, which is 2, which is just 0, minus on the top, so I get 2 times 3, which is 6, minus 0, which is just 6, times 1 plus 2 times y prime, 1 plus 4, all over x, which is 3, plus y, 2 times y, which is 0, so 3 squared. So this comes out to be negative 6 times 1 plus 4, which is 5, so negative 30, all over 3 squared, which is 9. And I can reduce this by 3 in the top and bottom, so I got negative 10 over 3. The answer is negative 10 thirds, which is A. Now 28 is the last problem. For t greater than or equal to 0, the position of a particle moving along the x-axis is given by x of t is equal to sine t minus cosine t. What is the acceleration of the particle at the point where the velocity is first equal to 0? Okay, so we have x of t given by sine of t minus cosine of t. And we're trying to find the first point where the velocity is equal to 0. So my velocity of t is equal to the derivative of my position, so x of t. And now I'm using our trig identities here. So the derivative of sine of t is cosine of t, and derivative of cosine is negative sine. So we get cosine of t plus sine of t. And I want to find when this first equals 0. So for cosine of t and sine of t to be equal to 0, this means that my cosine of t is the opposite sign as my sine of t. And I want to find the first point. So depending on how you're feeling with trig, this might seem confusing, but the easy way is to start to draw out your unit circle, right? And what I'm going to do is I'm going to make my way around the unit circle in the positive direction. I'm going to look for the first point that makes this true. And something that helps is if we think about our cosines and sines, there's one special triangle where our sine and cosine values have the same magnitude, and that's when it's a 45, 45, 90 triangle, right? So if you remember here, we have so the two sides, A and B, are the same length. So, call it A. And the hypotenuse is 1. Right. So this triangle has a special property where both the cosine and sine are equal to square root of 2 over 2. And I'll be making a video on the unit circle to help review this. But the sign here changes based off the quadrant we're in. So if you remember, cosine is x over r and sine is y over r. So whenever we're in a quadrant where the x values are positive, we'll get a positive root 2 over 2. And wherever the y values are positive, we'll get a positive root 2 over 2. So now let's quickly draw in all the 45, 45, 90 triangles. So there's one that's kind of there, and there, and there, and there. Something like that. Okay. So now in this first quadrant, the sign, x is positive, so we get positive root 2 over 2 for the value of cosine, and y is also positive, so we get positive root 2 over 2 for the value of sine. In the second quadrant, we get cosine is a negative square root of 2 over 2, and sine is positive because y is positive. 2 over 2. So right here, like we were just going in this positive direction. We've already found a value where the value for cosine is a negative sign as the value of sine. So what this means now is our first value of t that makes this equal to true, which means our velocity is equal to 0, is, we just need to figure out what this is in terms of radians or pi. So I know that this occurs at pi over 4, which is the 45 degrees. And so in the next quadrant, that's pi over 4 plus, what would that be? So here would be pi. So it's pi minus pi over 4, which is 3 pi over 4. So t to 3 pi over 4. That's the first value of t that has a velocity that's equal to 0. Okay. And now the question was really asking, what is the acceleration at that point? So now we need to find an equation for acceleration, which is a of t. And acceleration is equal to the derivative of velocity. So we just take the derivative of our velocity equation. The derivative of cosine is negative sine. And the derivative of sine is cosine. So now I just have to plug in t is equal to 3 pi over 4. Acceleration at 3 pi over 4 is equal to the negative of the sine value at 3 pi over 4, which we know is root 2 over 2. So it's negative root 2 over 2, plus the cosine value, which is negative root 2 over 2. So this gives us negative 2 root 2 all over 2, which gives us negative square root of 2. And that's our answer. Hey, perfect. And that's the end of this multiple choice section, which I hope wasn't too bad. So once again, if you enjoyed this video and these tutorials, please subscribe, like this video, or leave a comment down below. If you'd like me to solve a specific problem, feel free to send me a message with the problem you'd like me to solve, and I'll upload a video. And I hope you found this useful.